Well, thanks. I'm very grateful for the audience and for Linda's publicity. It's true that the contributions of my research group have been honored, but I'm not exactly a climate scientist. My interest is the carbon cycle. And this just tells you a little bit about where I came from. I was in the Sputnik generation, and we entered college in 1958, and okay, we're going to select a group and put you in a so-called honors program, which turned out to be a license to more or less mangle your education. I wrote a senior thesis, for example, comparing the 20th century novel in the United States and Great Britain. It was the most supremely sophomoric thing you could imagine. And my advisor said, well, Mr. Hayes, I notice you've taken a lot of chemistry. I think you should pursue that interest. It's an absolutely true story. And I went into chemistry and loved it and slid into the earth sciences. And my principal interest has always been the carbon cycle, which, as you can imagine, turned out to be good luck in the decades that I was trying to raise research funds. The carbon cycle became the flavor of the second half of the 20th century, if you were looking for research money. And better yet, if you were looking for good students. So I studied that, and I have been worried about the carbon cycle, and it is related to climate change. And I think that's the sort of hook that Linda was trying to pick up, and I just hope that it'll be useful. What I want to talk about is the really basic stuff about the greenhouse effect first. I have the impression that lay people in general understand the importance, don't doubt the reality, but don't understand exactly how it works. And my experience with students generally is that when you understand the nuts and bolts, it takes on a whole new level of reality for you. And so I'm going to start out by talking about the nuts and bolts. And it's an energy balance problem. And so then the question is, what happens to the energy? And the key point is that it doesn't just warm us up. It changes the whole global circulation and what we call climate, rather than just the temperature. These processes have been going on as long as we've had an Earth and a sun. And so there's a history to this that is, I would say, largely irrelevant, except that it serves as a source of confusion. And I'd like to try to clarify that. And then there's a separate question, which we may or may not get to. It's absolutely related, but it's fundamentally separate, and that's the acidification of the ocean. So those are the points that come up. Why do I say it's an energy balance problem? Well, here is my highly artistic rendition of the sun and the earth. We are practically a kettle sitting on a stove, constantly receiving energy from the sun. I mean, we understand that in our guts. Here comes the sunlight. Put on a dark jacket and walk around on a sunny day, and you feel it. Since we receive that energy, we would be constantly warming up unless we balance the budget by emitting energy, which indeed we do. Every physical body radiates electromagnetic radiation. The range of wavelengths in which we radiate that radiation depends on our temperature. If you're the sun at something like 6,000 degrees Kelvin, who knows what the temperature is in the inside, but the photosphere that is sending radiation out from the sun is about 6,000 degrees Kelvin effectively. If you're that hot, you're white hot. And as you cool down, you go to red hot and stuff like that. If you're the Earth, which is around 285 degrees Kelvin, that means like 12 degrees Celsius, you're radiating as well, but at much longer, invisible wavelengths. The Earth radiates in the infrared. So, we have here a body that's sending out visible radiation, and here's the Earth, which is emitting infrared radiation in order to balance the budget. And when we mess with the atmosphere, we are holding back that emission of radiation from the solid Earth. And as we hold back more of it, that's the nub of the problem. So I want to talk about how we hold it back. First of all, here's a picture of what's incoming. All right? This is power, watts per square meter on the vertical axis. And here's wavelength. This is a spectrum. The visible wavelengths are right in this range right here. And if the sun were exactly a 5,250 degrees centigrade, which is about, what, 5,500 Kelvin, black body, this would be its emission spectrum. What you actually see if you take a satellite up to the top of the atmosphere and look at the sun is this yellow figure. And what we get at sea level is what's shown here in red. The difference is radiation that's scattered in the atmosphere and partly reflected back into space. And here in the infrared region of the solar spectrum, there are big bites taken out of it by the absorption of energy by water. This absorption of energy, infrared energy in particular, by molecules is what plays an even bigger role when you talk about the emission of radiation from the Earth. Here again is energy on the vertical axis and wavelength on the horizontal axis. And this is this difference I was talking about, how the range of wavelengths at which you emit depends on your temperature. So here at short wavelengths, this is the sun radiating. Considerably longer wavelengths, here's where the Earth is radiating. At short wavelengths, the atmosphere is pretty much transparent. Nitrogen, oxygen, then, light goes right through them, no problem. Argon, light goes right through, no problem. At longer wavelengths, in the infrared, where the Earth is trying to balance the energy budget, energy is being absorbed by molecules, in particular by their chemical bonds. So here's a little molecular physics. Here's a water molecule, H2O. It sits there with these bonds to the hydrogen atoms vibrating. those bonds will absorb electromagnetic energy, provided, if and only if, that motion changes the magnetic dipole moment of the molecule. And as you can see, the overall average dipole is a positive charge out in this direction, a negative charge in that direction. The hydrogens tend to be positive. The oxygen, bristling with electrons, tends to be negative. So when that molecule does this, the dipole moment changes and water soaks up infrared radiation fabulously. No problem at all. CO2, on the other side, is a linear molecule. Again, the oxygens are negative and the positive is the carbon. And if that molecule sits there and just does this, there's no change in the magnetic dipole because the charge locations move complementarily and balance each other continuously. So that mode of vibration in CO2 is nothing to worry about. It doesn't filter out any infrared radiation. But there are other ways that CO2 can wiggle. And here they are. First of all, this is the so-called symmetric stretch. Spectroscopists sit around and they talk about the symmetric stretch and the asymmetric stretch and the out-of-plane bending, all this kind of business. But anyway, this is the one we just talked about. Here's an asymmetric stretch where the molecule's doing this. And if it does this, the dipole moment changes. And by the way, this involves the CO bonds, very strong bonds. So that absorbs like crazy in the infrared. Then there's this one, bending, where the molecule's just doing this, the carbons and the oxygens. That again changes the magnetic dipole. So this mode also absorbs infrared radiation. And this one is dangerous. That V2 mode occurs right in the middle of the range of radiation emitted by the Earth as we're trying to balance the budget. So what I have on the bottom here is a graph of the infrared absorption spectrum of a CO2 molecule. V2, that's this bending, comes where it really hurts, right in the middle of the Earth infrared emission spectrum. V3, which could be even more damaging, happens to come where there's not much radiation trying to get out anyway. So it doesn't matter much, that one. And these are overtones. They actually take a little bit, as we saw on an earlier slide, out of the solar spectrum. Any questions so far? Does it make sense? Okay? Do you feel better? I hope. Yeah. It's the CO2 molecule remains intact. It's just sitting there shaken. And when I shine an infrared photon on this molecule and it picks up extra energy, it goes from doing this to doing this, and then it relaxes back to the ground state by bumping into other CO2 molecules, which transfers energy to the atmosphere at large. And that's either heat or motion, which is the next point. Yeah. The point I'm trying to make, thank you. The things we're talking about are absolutely fundamental characteristics of a CO2 molecule. The molecule doesn't decide whether it's going to absorb radiation or not. It does it. I mean, a dye molecule, which absorbs energy in the visible range, it doesn't change colors. It always absorbs energy. It's always that color. This is the same phenomenon out at longer wavelengths, the CO2 molecule is always going to absorb energy. And this is the root of the scientific certainty about the greenhouse effect. You know, if you're putting more infrared absorbing molecules into the atmosphere, that energy is being deposited in the atmosphere. There are no two ways around it. The only question is, what happens to that energy? What does it do? It might warm us up, it might do something else. But there is utterly no question, you put in more absorbing molecules, more energy is going to be in the atmosphere.
No, it's absorbed instead of letting it.
Sorry?
Because it's absorbing the energy instead of letting it.
It's absorbing energy that's coming upward from the surface of the Earth. People have worked out very detailed budgets about energy coming in and energy going out, and we can measure it. I'll show you this, but then I want to move, well, sorry, let me go right ahead. This is what you see if you take a satellite up above the atmosphere and you look back at the Earth and ask the question, what's actually coming up? This is out of a research paper, so don't get too worried. The top frame is looking down at the Sahara Desert, which is hot. So the black body radiation curve from that part of the Earth peaks out at about 320 degrees Kelvin, nearly 50 Celsius, really, really hot. That's the effective emitting temperature. And if the radiation were escaping unimpeded, we would see this smooth curve. But what you see when you look is there are these big bites taken out of the energy coming up. And here's a huge one. This is that V2 bending bands from CO2, taking out this huge chunk of energy. So everything underneath this curve represents energy, and the part that's not making it up to the top of the atmosphere represents energy that's being soaked up in the atmosphere. And it's unbalancing, or it's impeding the balance and holding energy into the atmosphere, making it harder to balance the budget by radiating energy out into space. This curve is from over the Mediterranean, a little bit cooler, quite a bit cooler, 280 Kelvin, but again, you see the same things eaten out of it. This is over Antarctica. It's so cold, it doesn't look like a big problem, but there is still that absorption there. If I go back, here's what it looks like overall. This is the spectrum that the Earth would emit if the atmosphere were comprised, let's say, exclusively of argon or some other noble gas that didn't absorb any radiation. But the fact that we've got CO2 and water and methane means that these chunks that are represented by yellow are being absorbed in the atmosphere. That's always been going on, of course. There's nothing new about that. We've had all of those gases in the atmosphere for billions of years. The only problem is we're putting in more CO2 in particular. And as that raises the temperature, it, by the way, raises the amount of water, because you increase the temperature of the sea at its surface, and you increase humidity, which increases the amount of water. It's a feedback that makes things worse as you go along. So, what are the effects of the absorption of energy? If you think about irradiating with sunlight a planet, a sphere, sitting where we are, and you imagine, just for the sake of argument, that planet wasn't rotating. It was a shell of gas around a rock that was just sitting there. Well, the highest input of energy is going to be right at the equator. And up at the top, the radiation comes in at such an oblique angle that the amount of energy per square meter of surface up here is much lower. It means, big surprise, it's warmer at the equator and cooler at the top. That's going to drive circulation because at the equator, the warm air will be rising, and at the poles, the cold air will be sinking. And you'll wind up with a circulation about like this, if the planet's not spinning, if it's just a shell of gas around a stationary planet. But the Earth is rotating. This is the speed at Earth's surface due to the rotational motion. And here's the speedometer on the bottom. If you imagine that we could somehow completely disconnect the atmosphere from the planet so that the planet was spinning inside a stationary shell of gas, and you now held your hand out at the equator, you would encounter a wind of 1,037 miles per hour. That's the rotational speed of the planet. But of course, the atmosphere is frictionally bound to the planet. So the atmosphere, the shell of gas, spins along with the planet. But this imposes all kinds of forces. Imagine you're one of those sinking gas molecules up at the equator, and up the North Pole, and you're coming down, and as you're descending and as you're heading back toward the equator, the planet's spinning underneath you. So your pathway changes, and this is what you've probably heard of, the Coriolis effect. This is what the Coriolis effect is trying to explain, that you've got this turning planet underneath this gas shell. And the effect of this is that the very simple single circulation cell that you would expect in each hemisphere is just totally stirred up by the effects of the planetary rotation. And it breaks up roughly into 3 bands. Instead of just this one earlier, we saw gas rising at the equator, going all the way up to the pole, and coming back down. And what I'm saying now is that when you start spinning the planet, the turbulence induced is such that you wind up with it getting only to about 30 degrees before it just sinks anyway. And so you have these cells, typically 3 major bands, which define these things you keep hearing about, the trade winds, the prevailing westerlies, and the polar front. And this is obviously, if you ever watch TV weather, not something that stays put. We hear about the polar vortex wandering all the way down. This 30-degree marker, for example, is roughly the southern border of the United States, right? That's 30 degrees north latitude. 60 degrees north latitude is right underneath the curve of the Gulf of Alaska and through Stockholm and Norway, those parts of the world. So there's a lot of territory up here that has this circulating gas in it as well. And last winter we heard about the polar vortex sneaking down into Minnesota. So it was like 20 degrees out of place in terms of where it usually sits. But the energy that we see, or that's being absorbed, is what drives this circulation in the atmosphere, and as well the circulation in the ocean. I mean, we haven't even thought about that yet. The ocean is sitting there, and it's a fluid, it can move, and it's experiencing all kinds of gravitational forces that are strongly modified by the shapes of the ocean basins. And so to calculate how the ocean is moving around is a major problem. This is what people call geophysical fluid dynamics. And if you ask me, it makes nuclear physics look simple. It's a very, very difficult problem to calculate all of the effects, all of the forces that are driving these circulating fluids at Earth's surface, the ocean, and the atmosphere, and in particular, their interaction. So a huge portion of the energy goes not into warming, but instead to modifying, disturbing, enhancing, suppressing aspects of this circulation, which is to say, the energy goes into changing climate. And this is of huge consequence to our economic welfare and everything else. We can try to figure out more about what's going on. Here's what I just said. Absorbed energy affects climate, weather, as well as temperature. The problem is we can't go back and get weather reports, but we can estimate temperature retrospectively. For the past, oh boy, this is 20,000 years. There have been glacial cycles. So here is the LGM, is the last glacial maximum about 20,000 years ago. There are multiple ways we can quantitatively estimate the temperature as long as we've got ice. So that we've got ice up to about 800,000 years age on Antarctica. And there are indicators in the ice, the hydrogen isotopes in the ice cores give us a very good indication of temperature retrospectively. And we can thereby notice repeated glacial cycles back to about 1 million years ago. And you can look and see these things were periodic. And this is one of the straws grasped by people who say, well, look, this kind of variation in temperature is nothing new. It's been observed before. Absolutely true. There have been large variations, and they have been natural. And they've even, many of them, as you can see, been quite rapid, at least on a geologic time scale. So here's 1 million years, and you can count, what? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, yeah, that's right. About 13 ice ages numbered systematically through the past 1 million years. You can work back farther and estimate temperatures from oxygen isotopes in limestone shells, actually all the way back to at least the Cretaceous Tertiary boundary, and see there were times when it was really warm with palm trees growing in Antarctica and at high northern latitudes. So it has been much warmer in the past. You go back still farther, and these temperatures back to 550 million years ago are estimated from carbon cycle models and are much less secure. But we can certainly see that there has been a lot of variation in the past, and very interestingly, that for a good chunk of recent history, it's been periodic. And this is an interesting question. Why was it so stinking periodic? And this was worked out by Milutin Milankovic, a Serbian astronomer and physicist, who was fascinated by evidence literally dating from Egyptian times, bearing on the tilt of the Earth's axis. The Earth's axis, right now, it inclines 23.44 degrees relative to the plane of the ecliptic. It goes back and forth between about 22 and 25. Just back and forth a little bit. And the time scale, it's a periodic change in the obliquity. It's about 41,000 year cycle. But there are other changes. Jupiter and Saturn, orbiting beyond the Earth's orbit, affect the Earth gravitationally, and they change Earth's orbit so that sometimes it's perfectly circular and sometimes it's more elliptical. And so this goes back and forth like this. And that's a cycle of about 400,000 years. And finally, like any spinning top, the Earth wobbles. It precesses like a spinning top, and that's a cycle of about 21,000 years. Those things all affect the distribution of energy on the surface of the planet. The total energy depends on the sun. But as these orbital variations take place, the distribution of energy on the surface of the planet varies, and the distribution of energy throughout the year changes. And Milankovitch worked out the conditions that led to, or that favored, accumulation of ice. And he recognized that the key point was how much energy was being received in the northern latitudes around 65 degrees north, because that's where you've got both cold and dry land that will sustain and support ice. If you put ice on the ocean, it gets warmed up by the underlying waters, it can move around, it's not very stable. If you put ice on the continent and you have a cool summer, then that ice will tend to survive and you can build ice caps. So Milankovitch hypothesized that when you had minimal insolation, minimal reception of sunlight, or slightly less, let's put it that way, at northern latitudes, you had accumulation of ice caps. And he recognized that the periodicity was about right. Those three effects, the eccentricity, the tilt, and the precession, you can add them up and come up. This is what Milankovitch did. By the way, part of the time while he was imprisoned during World War I, he amused himself in his cell by working out efficient methods of calculation, paper and pencil, to do this and figure out how energy varied at these northern latitudes. And he came up with this now iconic estimate of the variation in solar energy received at about 65 degrees north. And then you look at the growth and decay of the ice caps, and the correlation jumps out at you. So everybody said, this guy's right. The major driver on these periodic ice ages has been so-called Milankovitch cyclicity. It doesn't turn out when you get, it looked really good between the First and Second World War. The evidence was so fuzzy that the precision and the match seemed to be perfect. But now we've got all kinds of data, so of course the wheels start to come off at least a little bit. But here is the past 420,000 years. This is a time of Earth history for which we have just exquisite records recovered from the Antarctic ice cores. And so we know how much carbon dioxide was in the atmosphere. You literally have gas bubbles preserved that you can analyze and tell how much CO2 was there. From the hydrogen isotopes in the ice, we have the temperature, and any knucklehead can see that the temperature is varying with the CO2. That's impressive. Methane varies as well. That's this line. And make sure I'm not telling a story here. These are the variations in oxygen isotopes in, I thought it was shells, but I can't read the subscript. It looks like it's saying atmosphere. Anyway, here's the insolation. And this is the Milankovitch energy cycle computed not with paper and pencil now, but far more precisely. And the correlation is still there. You can correlate ice ages with various features in the record, but as you can see, it wobbles. It's not as strong a correlation as it was. And it has to be said that the full story linking orbital variations and climate variations and the mechanisms that modulate it and make it vary, it's not perfectly understood by a long shot. But the variations are there, and there's no question that CO2 and temperature in particular have been tightly linked. CO2 is a really key point. It's a component of the atmosphere, and it relates both to a biological carbon cycle, where we've got plants turning CO2 into organic material, biomass, and we've got animals and other things turning organic material back into CO2. Photosynthesis and respiration. That's the biological carbon cycle. There's also a geological carbon cycle, where carbon gets buried in sediments at the bottom of the ocean. Those sediments eventually find their way up on the continents where they're eroded, and carbon gets pulled back into the atmosphere by these processes of erosion and volcanism and metamorphism. So this pathway of carbon flow from organic material back into the atmosphere transports, remember high school chemistry? Moles of carbon. It transports 7 times 10 to the 12th moles of carbon per year. And that's been going on at about that rate for billions of years, as Carl Sagan would say. Now, of course, we're doing something else. We're drilling down or digging down and removing organic carbon as fossil fuels, and we're burning it. So we're putting it right back into the atmosphere as mobile CO2. The question is, how does the rate at which we're doing that compare to the rate at which nature was doing it anyway? Well, of course, it's been increasing. Since about 1850, Industrial Revolution, huge amounts more. In fact, appallingly large amounts. The amount of carbon that we dig up and burn, these are the numbers from 2013, a United Nations report, more than 300 times more than would be recirculated just by nature alone. It's a huge effect, a great perturbation of the natural cycle. And it's caused, this is another one of these iconic figures. This is Dave Keeling's record of CO2 measurements at Mauna Loa, where in 1960, it was about 315 parts per million CO2, and now it's 400 parts per million CO2. On a scale versus, here's the past 1,000 years, CO2 measurements from the ice cores hovering right around 280 parts per million, the so-called pre-industrial level. And now, this is what we're doing. We've added hugely, this is the so-called hockey stick graph, in which the CO2 goes way up sharply at the end. And it was the data supporting this that was being refined and argued about by Michael Mann and others about 10 years ago, when their emails regarding exactly how to present it were grossly misinterpreted and led to all kinds of claims that the data were being cooked. And nothing could have been less true. So this is from a very recent paper by a whole lot of climate scientists. First author is a guy named Jim Hansen, an Iowan who was for many years director of the Goddard Space Science Institute in New York City. And it's again a time axis. Here's 1850 up to 2000. And here on a different time scale is thousands of years. So here's 400,000 years before 1850. And these are these glacial cycles that you saw on an earlier graph. And what's represented is so-called greenhouse gas forcing, the amount of energy being retained in the atmosphere by the effects of these greenhouse gases. And this is the so-called Vostok temperature, the ice temperature recorded by the ice core, the variations in the ice core. And if you can make them just absolutely congruent by multiplying the variations in temperature by 0.5. 0.5 is just to make it show how close the correlation is. Working forward from 1850, this line represents the forcing being added, the energy being added to the atmosphere by greenhouse gases, which means mostly CO2, also methane and nitrous oxide. And you can see that the forcing due to the greenhouse gases has risen steeply. Compare it to global temperature, which has risen not quite so much. And the reason, well, one reason for that is that the total forcing happens to have been cut way down by all kinds of particulates being put into the atmosphere as well, and especially by various volcanic eruptions, which have put lots of particulates into the atmosphere and modulated the total forcing. Although recently, the total forcing is now really beginning to approach the greenhouse gas forcing, and sure enough, temperature is rising as well. So this effect is definitely occurring. And the fact that the temperature is not following the greenhouse forcing or the total forcing as well as we might expect has to indicate that a lot of the energy has gone not into temperature, but into climate change. And we see that most recently, of course, locally, in the drought. And I'm afraid we might also see it in this year's El Nino, which was predicted to be, you know, this super El Nino that would get us huge amounts of moisture. This is from the Chronicle at the end of March, and it shows how the precipitation actually received at points ranging from Seattle down to San Diego compares not to a typical El Nino year, but to any year, to all years averaged out. We would have expected in this particular El Nino to have maybe 200% of normal precipitation. But as you can see, in the Pacific Northwest, they got about 150%. In Northern California, it's pretty close to 100%. Boy, it was noticeably better. But in Southern California, it was sometimes only 50% of normal, even though it was an El Nino. And the cause for that turns out to have been unusual persistence of high pressure off the California coast, pushing the moisture northward and keeping it from California. And we had in the really serious drought years, we had what was called the ridiculously resilient ridge of high pressure out there, which really dried us out. This year, it wasn't so ridiculously resilient, but it was still there. And the question is this now the kind of feature we're going to have to live with for a long time in the future, and we don't know. A key point, though, is that it's driven by CO2 for the most part. And my recipe would be to outlaw coal, which is certainly the largest contributor to greenhouse gas warming. I even see fracking as a potentially good step if it results in more production of natural gas, which can help us step away from coal. Mostly, I think I have to agree with Barack Obama, who made this summary. Climate change is a potential existential threat. It's a political problem perfectly designed to repel government intervention. It involves every single country, not a good idea. It's comparatively slow-moving emergency, so there is always something seemingly more urgent on the agenda. And we have to somehow collectively learn how to deal with that unprecedented circumstance and to work around it however we can. But let me stop there and answer any questions and hear any discussion. Yeah?
Could you restate questions or ask someone up to the mic so people who are listening to the video can hear?
What? I got an idea.
John, there's a microphone, a hand microphone in that stand right there.
Oh, but I'm going to stand there, and people asking questions can pass this one around.
John, I've read some articles in the chemical engineering literature that do some calculations of the reduction in CO2 that would occur if coal-fired plants were changed over to methane, which produces less than half the CO2 emissions. And some of those calculations, the authors indicate that the balance could actually be reduced. The overall cycle of CO2 includes absorption of CO2 by plants and other things and transfer to oxygen. That cycle, the increase could actually be reduced if methane were the fuel. And I was just wondering what you think about that.
I think it's true. I think that the use of methane as a power generating source is potentially very beneficial, especially because methane-fired plants can be engineered for quick startup and shutdown so that they could be used to fill the gaps that you get inevitably when you have solar power and stuff like that. So the danger is, or the point would be, it's still a fossil fuel. It would be better to not have to use methane. But methane is so much better than coal. Coal is less energy per mole of CO2 you put into the atmosphere, and coal plants are practically impossible to start up quickly and shut down quickly. So as long as you stay with coal, you're condemning yourself to persistent and high emissions. So stepping away from coal is the single most important thing I can see we could do. Yeah.
Here comes the microphone.
Sorry, here comes the mic.
Would, in place of methane, would nuclear be a better solution?
Nuclear is not a fossil fuel, and apart from the dangers of managing it, it's preferable even to methane. The difficulties are, it's a fissile material, and it has associated political and military hazards. If we could manage those perfectly, it would without a doubt be better even than methane. Fission power.
I just have a brief addition to that, which is that there's a huge problem with disposal of spent nuclear rods. Nobody knows what to do with them, and it's just a huge. The more of those you make, it just increases another really big problem.
I don't think the nuclear waste problem is scientifically insoluble. I think it's politically, practically insoluble. Believe it or not, I'm an oceanographer by my dearest scientific associations. If we put nuclear wastes into clays that were descending into subduction zones, I think we would never hear from them again. But people are so horrified by the possibility of using the ocean as a dumping ground for nuclear waste that it has proven always to be a non-starter. And in fact, I think it's the best single idea that I've heard. It's not cheap, it's not easy, but it's more possible and potentially much safer than any of the other. I can explain it in brutal ion exchanging detail if you want to know, but it's a good possibility.
When you explain it as clearly as you have, at least from somewhat of a scientific background, I find the arguments quite easy to understand, and yet, politically speaking, getting the public to accept climate change has been difficult, to say the least. It's up there with evolution. And yet, here there will be a meeting of all the Republicans in Cleveland, and I'll bet this will come up as if this doesn't exist. And so there are large economic reasons for why they don't want to believe it to be true. But I think there's also a lack of complete understanding about the scientific principles that underlie these problems. So can you expand maybe on what can we do to make this better? Is there an age belief difference as well between young people and what they're learning in school and older people? Are we getting any better in terms of education?
As a psychologist, I make a good geochemist. I honestly, what I was saying today illustrates part of my belief, and that is that if we could get people really to understand how utterly compelling and how fundamentally inescapable the basic physics of it are, that it would change things fundamentally. I think that people who have an understanding, but a shallow understanding of greenhouse warming, and who abhor so-called climate deniers, we need more of those, but I think we need, in particular, all kinds of people to understand the real nuts and bolts, so that they understand how this is not, the idea that there's a debate about it is just breathtaking. And as long as there's, any idea that it's debatable, then it's a license for economic greed to play a major role in shifting opinion. And so the key to it seems to me, is to clarify as insistently and patiently and carefully as we can the sort of absolutely fundamental security of our understanding of greenhouse warming or greenhouse effects on climate change. Yeah, Ron.
Hey, I may have missed something, but the high pressure ridge off the coast, do we know how that's related to warming or CO2? The fact that it's there and not somewhere else.
Yeah, this is the classic question of, is it really related necessarily to greenhouse effects? And the answer, I think, can now be probably, more probably than not, but there's no certainty. The fact that we know that all this energy is being retained, and we see there are scholarly studies, for example, of Atlantic hurricanes, demonstrating statistical significance rigorously in the power being released by Atlantic hurricanes, and a correlation between that and sea surface temperatures, and the sea surface temperatures clearly being driven by greenhouse warming. I know of no such analysis for weather systems in the Pacific. And I was pointing to it as being consistent with, rather than compelling evidence of, the effects of greenhouse warming. It is the kind of effect you would expect from messing with atmospheric circulation. But there is no chain of evidence that has been articulated. There's this marvelous grad student whose name I've forgotten at Stanford, who has made himself into a commentator on this whole issue. And I'm just echoing him when I say that it's more probable and that it's something we can point to as a likely effect, but not a certain one. Now, Jerry. Question is, what's the potential for solar and wind to help out? And I think the potential is terrific. They keep the rate of growth of these unconventional non-fossil fuel related energy sources. Each year it beats the prediction, and so I think that there's a very good chance. The difficulties that we have are a transportation infrastructure built on fossil fuels, and it's going to take decades to get away from use of gasoline and diesel fuel to drive transportation. That's just a huge problem, and solar and wind are not going to help us quickly with that problem. But I mean, they obviously are the sources to which we have to transition over time. Yeah.
If the burning of fossil fuels were stopped today around the world, how long would it take to change the atmosphere and the greenhouse effect?
A CO2 molecule that gets into the atmosphere stays there for about 5,000 years. So the E-folding time for the decline is long. But the moment you stop, you begin to see improved effects. Obviously, the most we can hope for is to just slow down the rate at which we're doing this, and that the fact that we're exceeding the normal flow of carbon from organic material to atmospheric CO2, we're exceeding it by a factor of 300, shows us how much scope for improvement there is and how much improvement is needed. There are people who they say, well, we're already locked in to various effects, and the reason they say we're already locked into various levels of warming is exactly this problem with the fact that if we stopped immediately, the CO2 would still be there and it would stay there for a long time. Um, the graph I showed with the forcing is from a paper by Hansen and about 20 other carbon cycle specialists dealing with what should we be shooting for? What level of CO2 in the atmosphere could be regarded as long-term safe? And their answer at that time was 335 parts per million. Now Hansen has chiseled himself up. He'll say, oh, maybe 350. But we're already well above that. Yeah.
I'm not a person, but I do have a question about the effect of global warming or climate change on animals in the ocean, animals and plants in the ocean. Are any species disappearing, or exactly what's going on in that?
Well, the biggest effect in the ocean at the moment is seems to be biggest effect in the ocean at the moment is not so much temperature. There are larval forms of some shellfish that are being killed off by rises of temperature in some parts of the ocean. That's happening. But the most worrisome effects are those affecting organisms that can't move. Corals are being one particular problem. And there you have two things going on at once. You have acidification and from the CO2 in the atmosphere going into the ocean, making the ocean waters more acidic and tending actually to dissolve the coral. And you have the fact that the organisms, in particular the algae living within the corals, tend to get out of the way, or literally to leave the corals when the temperature gets too warm. So you get bleaching events which are caused by increases in temperature, and you get dissolution caused by acidity. The strange thing about the acidity problem is that there have been times in the past when we had even higher amounts of CO2 in the atmosphere, and yet there were corals everywhere. And so the question is, how does that happen? And the answer to that is that in those earlier times, levels of CO2 rose so slowly that the acidity was constantly neutralized by erosion of basic materials from the continents into the seawater, so that the alkalinity balance was not disturbed. Now what's happening is we're putting CO2 up so fast that the titration mechanism on the continents can't react rapidly enough, and we're acidifying the ocean. So that's why that's a problem. It's the rate that's the problem there. So, you know, it's another reason. It's different from warming, but it's another reason we should worry about CO2 in particular. Yeah, David.
John, I wonder if you can help clarify this. It's an intuition that I've developed from somebody who hasn't taken chemistry since 1969. So that's a long time ago. But the problem is, and our contribution to it, if you burn gasoline in a carbon molecule is not that heavy, but when you combust it, it combines with two oxygen molecules which are much heavier. So the weight of the carbon from burning a gallon of gas is going to be much greater than the weight of the gallon of gas. Can you clarify that for me? Does that make sense?
No. I don't understand the question.
So I don't know what the weight of a gallon of gas is, but I think the weight of the carbon dioxide you put into the atmosphere from burning a gallon of gas is many times the weight of the gasoline itself. Is that true?
David's asking a question that's basically about units. People talk about tons of CO2, and they talk about tons of fossil fuel. A carbon atom weighs the same, whether it's a carbon atom in fossil fuel or a carbon atom in CO2. In fossil fuels, carbon is bound to hydrogen or to another carbon. And each hydrogen has an atomic mass of 1. In CO2, carbon is bound to oxygen, which is 16 times heavier than hydrogen. So if you use as your unit of comparison tons of CO2, counting the carbon and the oxygen, and compare it to tons of gasoline, then the CO2 weighs a lot more than the gasoline because oxygen is so much heavier than hydrogen. But that's irrelevant. The real point is the carbon. And so that's why I use these units that might curl people's hair. I use moles of carbon because that's what matters, is the moles of carbon, not the tons of CO2 or the tons of fossil fuel. And the reason for the weight discrepancy, which is, you're correct, but the reason for the weight discrepancy is just that oxygen is heavier than hydrogen. That's it. Sally.
I have a really simple question. When you fly, do you buy carbon offsets?
No.
you
Do I
think
buy
we-
carbon offsets?
Should we?
I don't know. I don't know about the offset business. I don't know whether it's being manipulated or whether it's really well run. The principle is a good one. Yeah, the principle of carbon offsets is sound. And the question is, are they actually being well run? I don't know. If they were being well run, then I would feel guilty by not buying them. So I protect myself by maintaining my ignorance. You guys are fantastic.